EECS 281, lecture number 17. Trees, trees, more trees. Spring 2020. We left off after dealing with the basics of binary search trees: insertion, search, and removal. Our summary left us with this in mind. In general, our operations and their complexity look like this: log n on average and linear in the worst case. And that's because all of our operations time complexity is based on the height of the tree. So in average case, our tree is stacked up to about log n high, but in worst case, we found that there's plenty of sticks that we can pick up and make this linear. So our next approach is to try to look at this height and see if we can't do something about it. Here's our definition of height from the other day. It's recursive. Of course, a tree is recursive. It's got a base case where the height of an empty tree is 0, and the height of every node after that is the maximum height of its children plus 1. Enter the AVL tree. This is named after its creator, Adelson, Velsky, and Landis. And what this is a balanced binary search tree. That's what it is. There's a number of ways to do it. Another one that's notable is a red-black tree. And a red-black tree is slightly more performant than an AVL tree. However, it's vastly more complicated. And since we won't actually be really implementing any of these anytime soon, we'll generally just be using our library implementations of it. It's important for us to understand how balanced binary search trees work, but it's not important for us to go deep into the guts of the best balanced binary search tree. So we're going to take this AVL tree because it is something that is very accessible, and it shows us the fundamentals of how a balanced binary search tree would work and why we would appreciate that. So, as I mentioned, it's a binary search tree. So let's start there. We've got a tree, which is really a graph. So I guess we start with a graph. Then we say we're going to make sure that this graph is a tree. Then we're going to make sure that this is a rooted tree. Then we're going to add the constraint that this is a binary tree, so each node only has at most 2 children. Then we apply the binary search tree property, which says that the left subtree is always going to be less than the root, and the root is not going to be less than anything in the right subtree. That's our binary search tree property. Then we're going to apply this height balance property. And it says for every internal node V in the tree, the heights of the children of V can differ by at most 1. That's it. It's fairly simple. Then when we run into a situation where this isn't the case, we're going to hold this height balance property as an invariant. So after we get done with any operation, then this property has to hold. If we get to a place where we're ready to finish an operation and we've got a place where one of the nodes V has a difference of more than 1 between its 2 sides, what we're going to do is use these things called rotations. And those rotations will correct the imbalance, and that'll get us back to our balanced tree. So what happens is once it's balanced, now we've got this worst case log n. Average case was already log n with our binary search tree. Now with our balanced binary search tree, we've got our worst case log n. And that should be music to your ears. So, at first glance, let's just figure out if we know what an AVL tree is when we see one. This height balance property, remember, every internal node, the heights of the children differ by at most 1. So tree 0, that one is trivially any kind of tree, right? It's got no nodes in it. How about tree 1? Well, remember that the height balance property is just a constraint upon internal nodes. So with no internal nodes, Tree 1 doesn't violate any constraints. Tree 2 is our first tree with an internal node, and you see there that it has a left child of height 1 and then no right child, or a right child of height 0. So 1 on the left, 0 on the right, difference 1. That makes this an AVL tree as well. How about tree 3? Well, starting at the bottom, we've got a leaf node, which just like in tree 1, was always going to be fine in terms of the height balance property. With no children, you've got no problem being balanced. So that's one thing we can always move forward with. Any leaf node is always balanced. How about node 2 here? Well, from the previous example, tree 2 is just a mirror of that. So if it was okay in tree 2, it's probably going to be okay in tree 3. So 2 and 3 are great. However, 5 has a problem, right? We see that in 5, it has a left child of height 2 and a right child, empty, of height 0. So 2 on the left, 0 on the right, difference more than 1. So this is not an AVL tree. Moving forward, there's a bit more stuff to look at here, but those same principles apply. You can see that our internal nodes in tree 4 are only 5 and 2. Those are the only ones that we need to apply this height balance property to. And 2 is a perfectly good AVL tree. And now, as we look at 5, we see 5's left child is height 2, right child height 1, difference of 1. We're going to go ahead with that as a good AVL tree. In tree 5, same thing. Now we've got an additional internal node. 2, 5, and 7 are all internal. 2 and 7 are mirror images of each other, and a duplication of tree 2, which we thought was great. So those look good. The only other internal node is node 5, right? And 5 has a left height of 2, right height of 2, difference 0, AVL to the max. How about tree 6? Say I've got internal nodes 2, 5, 7, and 9. 2 is great, 9 is great. 5 is actually okay. We got 5's left child is height 2, 5's right child is height 3, difference of 1, it's okay. But right here in the middle, 7 has a right child of 9 with height 2 and an empty left. So 0 on the left, 2 on the right. This is not an AVL tree, right? All right, so there's our basics of what we can see when we look for them. You should be able to pick this up fairly easily. We don't do a whole lot of proofs in 281, and this is no real exception. We'll give you the basics of this. I'll get right up to the real proofy stuff, and then I'll wave my hands and run away screaming. It's okay, though. So we'll start with H as our definition, the height of the tree. We already know how to calculate that. We're going to add this new thing, this N of H. And N of H is the key to understanding this proof. N of H is the minimum number of nodes. Notice it's underlined, italicized, and I highlighted it with my voice. So the minimum number of nodes it takes to make a tree of height H. So if I say, is this the minimum number of nodes to get to a height of a tree of height 2? No, I've got one extra node. I don't need this node to have an AVL tree of height 2. So in this case, if the H is equal to 2, then N of H is also equal to 2. So it starts out pretty simply, right? If you look at our basic tree, H is equal to 1, then of course N of H, the minimum number of nodes to get to a height of tree 1, also 1. Now, the tree that we see down below, that is a tree of height 3, this one right here. And I've clearly got enough nodes to get to height 3, so I don't need more. Question is, can I get to fewer, right? I'm trying to get the minimum number. So if I remove any one of these nodes, will I still have a tree of height 3 that is also balanced? Can't remove an internal node, so 2 and 5 are protected. If I remove 3, then my tree is suddenly no longer height 3, so that's no good. If I remove 7, then I end up with an imbalance right here at 5, because if I remove 7, 5's left is height 2, 5's right is height 0, not balanced. So 7 has to stay. So it looks like I can't remove any of these nodes and keep a balanced AVL tree of height 3. So in that case, I'm going to go ahead and say that h of 3 has an n of h equal to 4. So there's just some basic example of how I've got this n defined. And we saw here the base case is given to us as well. We can see that n of 0, an empty tree of course has 0 height, 0 nodes, and we've already shown 1, 2, and 3. So now we're going to try to extend this because we've got our base case, and of course this is in a tree, so we've got to have something that is recursive that we can keep moving forward with. All right, so clear up a little space here, and then I'm going to say for any tree that's greater than height 1, then the AVL tree has 3 parts, right? Anything that's taller than 1, an AVL tree with a minimum number of nodes has 3 parts. It's got a root, it's got a tall side, and it's got a short side. Even like I said, a tree of height 2, right? A tree of height 2 looks something like this, and you can see that it's got 3 parts. It's got a root, it's got a tall side, and it's got an empty short side. Because I'm looking for the minimum number of nodes, both sides can't be the same height. One side has to be shorter. And because I'm talking about a balanced tree, it's not just shorter, but it's exactly 1 shorter. All right? So then I can put all that together in my recursive definition and say that n of h for h greater than 1 is just going to be the root node, the side of the height of the tall side, h minus 1, and then the height of the small side, h minus 2. All right? So I can say that for this nifty little mathematical expression then, n of h in the non-base case is just equal to 1, the root node, plus the number of items in the tall side, plus the number of items in the small side. So there is where I'm going to get to leveraging my proof details, right? That's my number of nodes required. So then we can see how this will set us up in our height balance property. So with that, I've got h now. I've got n of h I've got n of h defined as a general concept, and then I've got n of h here defined mathematically. And let's go ahead and tack on n of 0 equals 0, and n of 1 is equal to 1. So there's a full mathematical definition because I've got to have those base cases defined as well. All right, knowing that, I can say that n of h minus 1, right, that's the tall side, has to be more items than the short side. That's a pretty simple definition. So if I take and add those two together, remember, n of h here is 1 plus a tall side plus a small side. So I can say if the tall side has more items than the small side, then if I add up 2 small sides, that's got to have fewer items than a tall side and a small side. So in that way, I can come up with this relationship here, n of h, because short side here and more than short side there. So if I add those two together, it's still not quite enough to get to the total weight. So I can say that n of h has to be greater than 2 times the number of items in the short side. That's what the boxed expression says. The number of items in the tree is more than twice the number of items in the short side because we've got to have a tall side, plus we've got to have a root. So there we go. So we can take that a little further and start working on how we apply this inductive step here. As I go to larger and larger trees, I end up with this expression here. And I mentioned we're getting right up to where proofing this happens, and then we're going to run off screaming. We've got this set up though, and as I start adding more and more layers, each time I go down a layer, I've got a chance to add these 2 nodes. So I'm going to keep multiplying by a factor of 2 as my height increases. So my inductive step then gives me something I can get to a closed form solution on, and then to solve that for h, all I have to do is take the log of both sides there, and I end up finding out that the height of tree is always log n. If you don't believe me, take 477. They'll knock it home. Or go find someone from the 203 staff, and I'm sure they would be happy to discuss this with you. They will make this certain that you understand it. That's me being silly. But yes, this is something that we don't have to prove as well. It's not something we're really going to be tested on either. I just wanted to make sure that you felt like I wasn't just claiming something that I couldn't prove. And I can prove this, but like I said, this is not our focus here, so I'm going to leave this one alone. But what I'm saying is, the takeaway is, because of this height balance property, because we know that the number of nodes in there has this relationship based on the height, I can say without a doubt, no matter what with a balanced binary search tree, this AVL tree is always going to have a height on the order of log n. That's great because, remember, my log n, or my height, my big O of height, was what mattered. That's what made all of my algorithms that I'm going to work on a tree, my search, my insert, my remove, those were all based on, well, how far might I actually have to go down this tree? And if we can keep that from going to n, then we can absolutely just beat plain old contiguous storage, right? Because our contiguous storage always had a worst case n. We wanted our tree to be better than that. Tree was better than that in the average case. Now with an AVL tree, it's better than that even in the worst case. So all of our algorithms in the AVL are pretty similar to the BST. We're going to start with how do I find things in the BST? Because remember, an AVL tree is a BST. It's just a BST that always keeps itself balanced. So search is the same as in the BST. I just start at the root, and if it's less than what I'm looking at, I go left. Otherwise, I go right. Easy. All right. Sort is, of course, the same as BST. All I have to do is fill up an AVL tree and then do an in-order traversal. That's great. Inserting the nodes is still going to be an insertion, which is still going to be based on the height of the tree. And now, since we've got this tree always at log n, I can say that every one of my insertions is no worse than log n, right? Worst case is log n. So if I've got n of those insertions, I can say inserting n nodes into an AVL tree is n log n. Great. My linear traversal ends up an additional n. I can say sort with an AVL tree is then therefore always n log n. That's great. Still seems like there's one lingering question here. How do we keep it balanced? A. And B, I guess that's more than one lingering question. And B, how much is it going to cost me? I suppose those are very related questions. It's every time we do something in 281, we say, how much is it going to cost? How much is it going to cost me in memory? How much is it going to cost me in time? So I need to know how to keep these things balanced. And if it's going to cost me more than constant time, then each insertion has to pay more cost than log n. So we're hoping we can get this done in constant time without too much hassle. So let's do AVL tree insert. It's going to start out like a BST insert. You just insert like BST. Then we're going to rearrange the tree to balance the height. That's where these rotations come in. The way that we can do that is each node has to keep track of its own height, and that's recursively easy. I get all the way down to the bottom of the tree, and the node that finds out it has no children and is going to insert the new node was a leaf node, right? Or at the very least had an open spot. So if it's a leaf node, it knew that its height was 1. If it wasn't a leaf node, it knew what its height was and that it had a right child or a left child, depending on where the empty side is. Right? So then as we try to insert some node below that, it's easy for that node to say, well, if I'm a leaf node and I just added a child, clearly my height is now 2. But if I'm an internal node and I'm adding a child to my empty side, I already know that I can ask my child what its height is, my existing child. And if that child's height is going to be no matter what it is, right? If it's a 1 and I add a child on the empty side, then I haven't changed the height of the parent node. If it's something greater, then I'm going to have no problem there either. But you say, wait a minute, if this was a balanced tree, no node can have an empty side and the other side with height greater than 1. So, as we add something to a node, this insertion point, the one node that's the parent of the newly inserted node, its height is either 1 because it's a leaf node, or it's 2 because it has one child. And adding the new node doesn't change its height. So, then as this insertion is done recursively, you can see that after you've added the node to your child can report back to you what its new height is. And if that new height changes your height, you can change your height and report back to the node who called you. It's all incredibly recursive and fun. But the good news is it's not too hard to manage if everyone keeps track of its own height. And then as you do an insertion, you update your own height accordingly and inform your parent. So then we've got this new thing we're going to call a balance factor. And this balance factor is just a number that we get from subtracting the height of the right child from the height of the left child. That's it. That's our balance factor. And the balance factor, in order for us to stay balanced, has got this constraint here that it has to stay within this tight range of -1, 0, or 1. So that means I can have these three things as balanced trees. Come on, there we go. So those are all balanced trees, right? Because you see that the height difference here is a +1. I've got a 1 on the right, a 0 on the left. Sorry, a 1 on the left, 0 on the right. Here I've got a balance factor of 0. And then here I've got a balance factor of -1. All of those are balanced trees. We said that we were fine with those looking like AVL trees. So this is just a way to codify it, to give us a rule, to give us some numbers to look at. So we say anything that's greater than a +1 or less than a -2 balance factor is out of balance. And in reality, it's never going to get beyond that, because as we do some behavior, we're going to set this thing out of balance if we do. If we set it out of balance, it's going to be a +2 or a -2. Then we're going to fix it, and it's never going to be bad again. So, balance factor, example. And the easy way to get to the balance factor is to first get your heights out there. Right? That's the easy way to do it when you're first doing this, practicing. Later on, it'll be something that you can quite easily handle by inspection. But for starters, what I'm going to do is I'm going to go and draw in my heights. All of my leaf nodes always height 1. This internal node is height 2. And then you can see that the parent node is the max of those plus 1 gives me a height 3. Great. So now that I've got my heights in there, I'm going to go back and set up my balance factors. Right? The balance factor of any leaf node, always 0. I can just draw those in right away as well. If I look at this node 2, we see that it's got a left child of height 0. Empty child is always height 0. 0 minus this 1, which gives me a -1. So I can see that it's balanced at 2. And same thing at 5 here. I can say this 2 minus 1. That's going to be a +1. So every node in this tree has a balance factor that is in that range of 1 to -1. So I would say that this then is a balanced tree. That's good. How about this next one? Same sort of thing. Let's get our heights in first. That just makes our life easy. 1 for the leaf nodes, 2 as we work our way up. There's a 3, and 5 has got the max of those plus 1. Looks like that. Hopefully you already see that this isn't a balanced tree. But doing the math always helps. Leaf nodes got a balance factor of 0 by default. This 3 has a -1. This 2 has a -2. There's our problem. And then if I look at the root node, I can see that one's got a positive 2. Oh boy. It's got a positive 2, but it's also unbalanced, right? So I've got 2 places where this tree is out of balance. Good news is, if I fix the one, I will fix the other. So you can see here that this then is not an AVL tree because it's out of balance. Because it's got a balance factor here of -2 and a balance factor here of +2. Both of those are invalid balance factors for an AVL tree. So here's a balance factor example. And these little simple trees have some values in those nodes. And the values in those nodes aren't the node values. Those values are actually balance factors. So if I look at the balance factor of each of these yellow, purple, and cyan nodes, you see how their balance factor shows up, right? This has got a balance factor of -2 here because there's a height of 0 on the left, a height of 2 on the right. 0 minus 2 gives me -2. That's a -1 and 0. You can see all of those. Here I've got something that's going to be interesting for us as well. It's got a -2 because it's still got a height of 0 on the left and a height of 2 on the right. But this node, this other internal node, has now a height of 1 on the left and an empty or height of 0 on the right. So this gives me a +1 balance factor. So that's just an example of what those trees look like in shape with their balance factors attached to them. All right, quick example. Exercise, pause, do this one at home. If you want to be good at this, practice. But until you are, start by drawing in the heights, then you get your balance factor after that. Life is good. Height 1, height 1, height 1. I always go sort of breadth first because I look for my leaf nodes and deal with them. Then I work my way up. So this is going to be a height 2. There's a height 2. It's a height 3. There's a 2. It makes this 4. Once I've got my heights in, it's pretty easy to calculate my balance factors. Once again, I go breadth first and look at all of my leaf nodes just to simplify my life and get them down to 0. And then I can go up and keep calculating my way up. This one's got a -1. This one's a 0. 1 minus 1. This one's got a 0. Here I've got a 0 as well. And finally, what I end up with is a +1. And I'll keep writing the pluses in there just to be very explicit. But +1 and -1 is good. So this looks like a perfectly well-balanced tree. That's good. I'm happy with it. All right. So let's do an insertion here. We're going to go from the root and insert 14. Say, well, I'm looking at 15. It's less than that. Let's go left. It's not less than 6, go right. Not less than 7, go right. Not less than 13, go right. Oh, wait, we've got a null pointer. Then this is where we insert the 14. Now, I don't have to worry about throwing a lot of things out of balance, but when I do an insertion, I'm going to go from my insertion point back up to the root. That's when I know that I've gone in and come back out cleanly. So if I do that on the way down, I'm going to say, hey, look, here's a new node. And since it's a new node, it's a leaf node, it's got to have a height 1. 13 previously had a height of 1. So as it's working its way back out, it says, well, now I have a child. I must be of height 2. And I return that to my parent. My parent 7 said, well, my height was previously 2, but now I've got a child whose height is 2, so I must be height 3, right? As same thing goes with the 6, it comes up with a height 4, and this would all be height 5 if we worked our way all the way back up to the root. We don't do it quite in this order. We're going to be working our way up, and as soon as we see a problem, we're going to fix it. But you can see how if I travel all the way up from insertion point, right? I came here in the 14, that's where I inserted it, all the way back to the root. You can see that this is the only path where trouble can occur. Over here to the left, this little subtree is completely undisturbed. If it was balanced before, and it had to be, it was an invariant property, it's still balanced. If this is balanced, right, it's unaffected by this insertion. So then to fix my balance, you can see that it's only up this path that I came down where I might have to do something, right? Any other thing might cause problems with something else. So I say that I'm unbalanced here, and I need to figure out how to fix that. Enter the rotations. We're going to use these rotations to rebalance our tree. What we do is we, at the high level, we're just swapping a parent and one of its children to sort of fix our balance. Caveat, we don't want to break the BST. This is at fundamental level, and AVL is a BST, so we have to maintain the BST property first and foremost. Then we keep the height balance property as well. on top of that. So now I'm going to come up with a rotation here. And you see that this tree on the left, this is definitely unbalanced. 5, left height is 3, right height is 1, out of balance. I can fix this one. You can see I've got a fixed version of that over here on the right-hand side. Same 5 nodes. Same root node, actually. And I've gone and pulled my balance factor up to +1 or 0 everywhere. So this is what a balanced version of this looks like. And the key part about this rotation, remember I said we're going to apply these rotations so that we can guarantee that we're balanced. And if we can do that in a constant amount of additional work, then we don't lose our great time complexity. And the rotation is something that is a local change that involves at most 3 pointers and 2 nodes. That's great. That sounds constant to me, because if I've got a tree with 500 or 5 million nodes in it, every rotation is still a local change that involves 3 pointers and 2 nodes. The number of pointers and nodes doesn't increase with the number of nodes in the tree, constant time. All right, the easy part is what a rotation is. You just interchange the role of one parent and one of its children. So we've got some imbalance. We're going to say, hey, the child that's to the tall side, if I pull that child up and send the root down, it's kind of just like rotating things away from the imbalance, right? Then we just have to keep track of the BST property. And the second part is hard part, and we've got these 2 statements that are fairly cryptic. So just to make them feel better, I like to read them very fast. The right rotation, we copy the right pointer of the left child to be the left pointer of the old parent. And you got it, see? The left rotation, we copy the left pointer of the right child to be the right pointer of the old parent. Let's move on. No, we'll be back, because these are a little bit cryptic, like I said. Once we see it, you go back and read these executive summaries of what a rotation is, and life is good. So, here's my basic rotations. I'm going to show these rotations 3 different graphic sets just to make sure that they work for you here. So I've got this unbalanced tree here, right? And I'm going to rotate right. That's what this column is, my unbalanced tree, right? Here it is unbalanced, and then after my rotation it ends up balanced. So I talk about interchanging the role of 2 nodes, right? I've got a parent and a left child. After the rotation, the parent is now a child, and the left child is now a parent. That's the role reversal that has taken place, right? But we also have to maintain this BST property. Here's our rotation left. In our rotation left, we see that the parent has come down and the right child has become the parent, right? Go back and say, in a right rotation, we copy the pointer of the left child to be the left pointer of the old parent, right? The pointer to the left child, I said that backwards. In the right rotation, I'm copying the right pointer of the left child, right? Copying the right pointer of the left child to be the left pointer of the old parent. So this thing is going to be sticking out of here when we get done, because this is the left child of the old parent. And you can see here that that's exactly where it is. So the right pointer of the left child has become the left pointer of the old parent, right? So right pointer of left child, that's here, has become the new left pointer of the old parent. And then the reverse of that is true when I look at my left rotation. I copy the left pointer of the right child to be the right pointer of the old parent, right? The left pointer of the right child is now going to be the right pointer of the old parent. So that is done because it maintains my BST property. That's why that's done. Look at where this purple triangle ends up, right? It starts out to the left of P. It must be less than P. It also is then to the right of LC, the left child, because it's greater than everything in LC. When I get done, if BST is preserved, then those two relationships are also preserved. And I look down here, and where do I find this purple triangle? It is still to the right of the left child. And it is also still to the left of the old parent. So we can't have lost our BST property. Those relationships are retained. And in this particular drawing, we see these circles represent nodes, and the triangles represent an entire subtree of some height that's undetermined, right? So we don't even know. That could be many, many nodes. But even if it is many nodes, all of these purple nodes have to be greater than or not less than LC. So they have to be to the right of LC, no matter how many of them there are. And same thing, no matter how many of them there are, they all have to be less than P. So if I retain that after the rotation, then my BST property is protected, right? And the same thing is true in the mirrored version over here on the right-hand side, and you're good to go. So let's use our rotations to balance these trees. I started out and said I was going to interchange the role of a node and its parent. So if I'm going to rotate this one, I think I need to rotate this one to the left, right? Because I see that I've got a tall right side and a small left side. So if I want to balance this out, I have to take things from the right and move them to the left. So that's how I think about it. I think when I've got an imbalance that's negative, then I'm going to rotate some things left. All right? So the way that I'm going to notate this, I'm going to call this a rotate left around A. And that rotate left around A is going to just interchange the role of A and its right child. So B will be up and A will be down. A has no other children. B already had a right child. So if I keep that around, you see that my BST property is maintained, and now balance is achieved. I've got one internal node, B, and it is got equal sides on it. It's got equal children, right? All right. So next step, we look at this next one. What's going on here? It's got a negative balance factor at A, sure. I can see a height of 0 on the left, a height of 2 on the right. So it's negative balance. If I try to crank this thing around to the left, and I do a rotate left around A, what happens? I interchange the roles of A and C. So C goes up, and A goes down. But I have this problem. C already had a left child. I can't just put A there without doing something with C's left child. I said right child, I meant left child. C already had a left child, so I can't just make A be C's left child without some repercussions. So in our complicated description here on a rotate left, remember we said copy the left pointer of the right child, so that's B in this instance, to be the right pointer of the old parent. Left pointer of the right child to be the right pointer of the old parent. Right pointer, old parent. So that's what my rotation looks like. And, unfortunately, I don't feel very balanced. My BST is protected. You can just look at these in terms of the actual letters that they are. C is not less than A, right? So it should be here. A is less than C. It should be there. What about B? B is less than C, so it should be in C's left-hand side. But B is not less than A, so it should be in B's right. So that's a perfectly good binary search tree. It's still just not balanced. So what I'm going to need to do here is, because I've got this zigzag, you see I'm just going in one direction here. Here I'm changing direction, right? So with a zigzag, what I'm going to need to do is I'm going to have to do some additional work. Sound like it's getting dangerous, messing with my complexity, but it's not going to be too bad, because what I'm going to do here is, before I rotate left at A, I'm going to rotate right at C. And I can figure out how to do this if I look at my balance factors attached, right? Balance factor here was 0. Balance factor here was +1. Balance factor here was -2. So I said a negative balance factor is going to require me to rotate left. So this -2 is going to demand that at some point I always rotate left around A. However, in this early case, I had a balance factor of 0. Here I had a -1. Here I had a -2. I was fine with just rotating left around A, and it fixed things. Because I've got this sign change here, negative, 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 positive, with a sign change, we call this a zigzag. With a sign change, I know I've got to do 2 rotations. So it's 2 rotations now. Still messing with, at most, 3 pointers and 2 nodes, just twice. So even in terms of constant amount of work, this is twice as much work as before, but it doesn't grow with the number of nodes. So it's still more work, but it's still constant work. So if I rotate right first around C, right, first around C says first let's apply this rotation in there and interchange B and C's roles. So I end up with a tree after the RR that looks like A, B, C. And that's great. But I determine before I start these rotations what work needs to be done. Then I do the work, and then I check to see if I'm balanced. So I don't even do any more checks once I've done this rotate right. I know already that I'm going to do a rotate left. Now I can go ahead and do the rotate left around A, and we have already done that. It looks like this thing over here. So when I've got a zigzag, I've got to apply 2 rotations, and that zigzag is a sign change. When I've got a +2 or a -2, a zigzag happens when below it I can find a -1 or a +1. There we go. This is just walking through what I did. Which leaves me then with these 4 cases, right? I've got easy situations where I've got 1 rotation, either a left rotation or a right rotation. Then I've got my 2 zigzag cases where it's +2 -1 or -2 +1. And both of those give me a double rotation where I'm going to do some rotate right followed by a rotate left, or a rotate left followed by a rotate right, and I'm going to fix my imbalance situations. So here are some examples from CLRS documentation. You can see that it's got that CLRS illustration style here. And the difference between this one and the colored one that we had on the previous slide is this one is actually drawn to scale. Right, you can see that those subtrees, same sort of thing here. I've got these ovals that represent actual nodes, and then these triangles which represent undefined, or undescribed, I should say, undescribed subtrees. What we do know about them is their actual heights, and you can see how this one being drawn to scale, you can see the imbalance here because I've got a difference in height on A, right? If this is the height of its left child, then the height of its right child is 1, 2 more. So this is going to be something that's got a negative imbalance here. It looks like a -2 at A. So if I'm going to do a left rotation around A, I'll get that balanced out. And to do that left rotation around A, I'm going to interchange A and B's role. A and B have swapped here. A is the child, and now B is the master. Okay, sorry, there's a small Star Wars reference there. But B has gone to the root position, and A has dropped down, right? And what I can do then is see if these triangles are drawn to scale, these subtrees are drawn to scale, if I retain my BST property, right? How do I make sure that I do that? We see that everything in T1, T2, and T3, those are all greater than A. Right, because they're in A's right subtree before we even started. So T1, T2, and T3 all have to be to the right of A. And then the only other thing that's going to change here is, or going to be in the area that gets changed, is you see that T1 is less than B when we start. So it's already to B's left subtree. So when I get finished, it has to retain that. And you see that over here after the rotation, T1 is greater than A, to its right, and also still less than B to its left, right? The things that don't change, A's left subtree hasn't changed, B's right subtree hasn't changed. But now, since these triangles are drawn to scale, you see that every node in this, if we think of these triangles as being balanced subtrees already, then the distinction here between T1 and T2 is just, T2 and T3 is just 1 step. So this is a balanced C. A is clear. B is very clearly balanced as well because its children's heights are based on either T1 or T0 and T2. All right. The one below that is just the mirror image of that when I need to get a single rotation. So I like these diagrams as well because they are so drawn to scale. here's what the double rotation looks like. And the double rotation is 2 steps. And this is great because now you can see how this zigzag comes about. You can see these blue edges here. Those are the ones that outline the actual zigzag. I've got a negative balance factor here at A because it's a 0, or sorry, it's a whatever this is, we'll call this T. T on the left, and then T plus 2 on the right. So that's got a negative 2 balance factor. Then if I look at what's going on at C, we see that C has a height of T on the right and a height of T plus 1 on the left. So this is going to be a plus 1. So there's my zigzag. I go from a negative sign to a positive sign as I work my way down through this imbalance. All right? So to fix this, I'm going to first rotate right here, and then I'm going to rotate left there. So step 1, rotate right about C. It gives me this, and now I can see I've got it looks like it's even worse, right? This is why you don't want to try to figure out how to fix things in the middle of a double rotation, because now I see that B is unbalanced. If I fix B's imbalance, it's not going to fix A's problem. So I don't want to mess with that, right? Because fixing B's imbalance is just going to rotate B and C back the way it was before, and it's not going to fix A's problem at all. But since I know that I was going to rotate right around C, then rotate left around A before asking any additional questions, I can see that the first rotate right has actually even kind of made things worse, right? I've got a height of T over here on A's left, T plus 1, T plus 2, T plus 3 on A's right. It's worse now, but since I know I'm going to do this rotation afterwards, I've got that rotation that fixes things. Now I interchange A and B's role, and I end up with this tree that looks balanced. And you can go back and verify your BST property being protected, because you know how T0, T1, T2, T3 all relate to A, B, and C. T1, T2, and T3, of course, all as before, were all greater than A. So they should all, any of them, if they end up around A, should be in A's right side, and they are. T2 and T3 were all greater than B. Here they still are. And T0 was, of course, less than everything. It's still less than A and B and, of course, C. So now I've got this balanced tree. The next slide is just the other double rotation. Here where I start out a tree that's got an imbalance, and it's got a zigzag that looks like I've got a plus 2 at C, if you count them up, and I've got a minus 1 at A. So this is a left-right zigzag, and so I'm going to fix that by rotating left and rotating right to fix it. All right? All right. So here's another illustration. This one also drawn to scale. This one is drawn to scale and with color. It's like a combination of all those good things. But you can see here's my 4 cases. Here's where I just need to do a left-left imbalance correction. I'm going to rotate right to fix that. Here I've got a right-right imbalance, so I'm going to rotate left to fix it. Here I've got a left-right imbalance, which I rotate left and rotate right to fix, and a right-left imbalance, which I'm going to rotate right and rotate left to fix. And then at the end, you can see all of my illustrations here with my 3 sort of colored nodes. Those are the ones that are nodes. And then I've got sort of black and white or grayscale triangles, these grayscale subtrees. All of those are the same height, and I can see how balance gets retained. All right, check and balance. Let's figure out how to get this done. This is a part of insertion. So as insertion is finishing, right, after the recursive call. So the recursive call is, hey, I need to insert this, but it's less than me. I'm going to insert this into my right child. So that's the recursive call. Before the return of that happens, like when that call returns to the calling function is going to do this, right? So calling function is the calling function says insert into my left subtree, and when that returns, I'm going to do this before I return to the parent that called me. That's this check and balance. And this simple pseudocode lets you see here that I've got the basics. If my tree is out of balance, it's a plus 2 or it's a minus 2, because that's all it can be, right? We could have put equal in there, but it's just sort of a protection thing to put greater than plus 1. We know that after a single insertion, if it was already balanced, it had to be a plus 1, minus 1, or 0. I can never be worse than a +2, -2, or 0. So if I say my balance is greater than +1, what I'm really saying is if I just inserted this and now my balance is +2, to fix a +2 balance, I am going to rotate right to fix that. You can see that here. And to fix a -2 balance, I'm going to rotate left. No matter what, eventually that's how you fix those imbalances. But inside each one of those branches, I've also got another little if there that says, hey, I know that if I've got to do this to fix it in the end, that's what I'm going to do. But what I need to know is if this was achieved by zigzagging, because if there's a zigzag, I've got one step that has to happen first. So check and balance says, look, if I've got a +2 imbalance plus a -1 imbalance below that, then what I need to do is do a rotate left first, followed by a rotate right. Yes. Same thing here. If I got a -2 with a +1 underneath it, I'm going to rotate right and then rotate left. So this then is what I get. What's the complexity of this check and balance? Complexity is clearly constant. There's no inkling of how many other nodes are in the tree. All we're looking at is, hey, what's going on with my child? We've already discussed that these rotations are constant time. So then, how many nodes could I possibly need? Right? After an insertion, it turns out that no more than one fix is needed. And that fix could be a single rotation or a double rotation. But there's never any need to do more than that. So because check and balance happens inside of insertion, it's going to happen all the way back up to the root. So you insert starting from the root, you work your way down, left, right, find your insertion point, insert there, and then after the insertion takes place, as part of insertion, I should say, after the actual node creation and attachment happens, then you're going to check and balance your way back up to the root, because every call has check and balance built into it. So the check and balance works its way all the way back up to the root. Eventually, after we've found our first problem situation, if one exists, if we find a problem, we correct that. It doesn't matter how many nodes above this were put out of balance with the insertion. Correction of the problem at its first location coming from the insertion point corrects the imbalance all the way up to the root. And that's pretty great. All right. What happened on that one? All right. All right. So that's what this check and balance is. This is just a discussion of that. Outermost if question, is the node out of balance? Left too big, right too big. And then we do the double rotation if the signs disagree. All right, so here's our exercise. Let's rush through this one. You can do this one on your own. And this is a great way to start thinking about how might I be tested on this. Sure enough, right? Can we do this insertion, right? Here are these nodes, these values I'm going to insert into a tree. 3, 2, 1, 4, 5, 6, 7, 16, 15, 14. And below it, I've got a nice chart so that you can look at the rotations that you need to do if you need to do them. But what we're going to do is try to do these insertions in order. And then every time we do an insertion, right at the end of that insertion is when we check and balance to make sure that before we even get done with the insertion, we've got a tree that has our height balance property guaranteed. So let's get started. Right? We start out by inserting 3, 2, and 1. 3 goes in. It's got a left child of 2, and 1 comes in. I say, oh, wait. After this insertion, I'm now out of balance. As I work my way up from the insertion point, that's fine. That's fine. That, not so fine. So I do a rotate right around 3, which interchanges back. Interchanges 2 and 3's role, and 2 retains 1. And I get a tree that looks like that. So that's what it looks like after my insertion there. Next up, I'm going to insert 4, 5, and 6. So that looks like this. I had 2 over 1 and 3. If I insert 4, that's just fine. If I insert 5, now I've got 2 locations where I've lost my balance. I'm imbalanced there at 3, and I'm also imbalanced at 2. Good news is, fixing it at 3 will also fix it for 2. And you can see all I need to do here is a nifty little rotate left around 3. Rotate left around 3 swaps 3 and 4's positions. So 2 doesn't point at 3, it now points at 4. And since 4 didn't have a child, we're bringing 3 down there, 5 that way. There's my 1, and that's what my balanced tree looks like. All right? So that's inserting 4 and 5. I fix my balance by rotating left. After that, I need to insert 6 and 7. So if I insert 6, it looks like that. And then what do I feel about my balance? Well, 6 is balanced, 5 is balanced, 3 is balanced, of course, is a leaf node. 4 is even balanced, that's looking good. 1, another leaf node's got to be balanced. However, after inserting 6, I do have an imbalance right here at 2. That's not so good. So let's then figure out how can we rotate this. Since this has got a -2 imbalance, and I work my way down here, I've also got a -1 imbalance. So there's no zigzag going on there. Or not a -1 imbalance, a -1 balance factor. So I'm going to rotate left then around 2. Rotating left around 2 interchanges 2 and 4's role. So 4 goes up, 2 goes down. That we already had. Some things don't change, like 2's left side and 4's right side. What then happens to 3? 3 used to be attached as 4's left child, and we know that the left child, the left pointer of the right child becomes the right pointer of the old parent. So that's going to drop the 3 in right there. And that makes good sense. In terms of binary search trees, everything is good. I've got balance. I'm happy with it. That's what happens after a 6 insertion. Now what happens after a 7 insertion, right? I'll put 7 down here, and you can see that almost everybody's balanced. 6 and 7 are balanced. 1, 2, 3 is balanced. Even 4 is balanced. But 5 is not balanced, right? 5 has a height of 0 on the left, height of 2 on the right, so I'm going to have to rotate left around 5 to fix things, right? And that's just going to turn that into a sort of a 6 over 5 and 7. And if I insert that thing below my 4, keep my 2, 1, and 3, you see I've got some nicely balanced tree there. So this one's a rotate left around 5. That fixes things. We'll do some more insertions. We still have only done simple insertions, simple rotations. A rotate left, a rotate right. But as I insert some more stuff in here, let's see. I got 4 over 6, 7, and 5, and 2 over 1 and 3. I'm going to put in 16, 15, and 14. Throwing in 16 is no problem. 15 comes down here, and I see I've certainly got some imbalance. 7 is imbalanced. 6 is imbalanced. 5 is imbalanced. But the fixing it at 7 is going to fix it for everybody. So how do I fix it at 7? I have to note that 7 has a balance factor of a -2, but its child 16 has a balance factor of a +1. So there's my first zigzag. So I'm going to fix this by first rotating right around 16, then rotating left around 7. All right? That gives me a tree that looks like this. Rotate right around 16, rotate left around 7. Now I've got a balanced tree. You can see that this tree has got all of those nodes that I had in there already. The structures that were already in place before I got down that low, all of this stuff, right? All of this stuff is basically unchanged because there was no problem with it before. And then the stuff that we added, 16 and 15, caused the problem. We fixed them, and we're good to go. Last thing we have to put on is 14, so I'm going to start at 4. It's not less than 4, go right. Not less than 6, sorry, go right. It's less than 15, so let's go left. But it's not less than 7, so we'll go right. So our tree then ends up looking like that. How does that feel? Working our way up from 14, no problem. Leaf node balanced, 7 balanced, 6 balanced, 15 balanced. 6, however, has lost its balance. And for that matter, so has 4. So we have to fix those, and I'm going to fix that by coming into where my problem first occurs. Problem first occurs at the 6. We see that 6 has got a height on its left of 1 and a height on its right of 3. So we're going to call this a -2 balance factor. And then as I work my way down to the insertion point, I inserted here. I need to check that child. I don't need to check 6's left child because that's not where insertion happened. Insertion happened to the right of 6. So what's the balance factor of 6's right child? It looks like that's going to be a +1. So there's where my zigzag is, my sign change. 6 has got a -2, but its child of import has a +1. So there's where the zigzag is. I'm going to first rotate. I'm going to have to rotate some stuff this way, or rotate left around 6. But to do that, I first need to rotate right around 15. So you see my fix then is a rotate right around 15, a rotate left around 6. This is what I end up with, my final tree after inserting all those nodes. You can probably now just do a quick inspection. If not, go back, assign some heights, assign some balance factors, convince yourself that this is a balanced binary search tree. How about removal? We already talked about removal. That was a complicated step that we did at the end of the previous lecture. So we're going to start there. We're going to do that same removal that we did. We're going to go find the in-order successor, replace the node to be removed with the in-order successor, and then remove the in-order successor. The in-order successor is always going to be easy to remove from the tree because it's going to have at most one child. And we know that removing a node with one child is easy, and removing a node with no children is trivial. So after we swap that out, we've got easier or trivial work to make sure that it's fixed, but we can throw ourselves out of balance as we shorten one side or other in the tree. So we did that. We did that with our in-order successor. Now, let's check it out. So the removing in the AVL tree has done same as before. This tree looks a little sparse on the left, a little heavy on the right, but it's not unbalanced, right? Leaf node 32 here, balanced. 17, one child, balanced. How about 44? 44's got height 2 on the left, height 3 on the right, so 44 is balanced. 62 is clearly balanced. It's 50, yeah. It looks a little sparse on the left, but it's still actually balanced. So if I remove 32, that was a trivial deletion because 32 has no children. So all I have to do is just delete it. But what you're going to do in your removal, just as in your insertion, after you do something that modifies the structure of the tree, you have to work your way back up to the root to make sure you haven't thrown anything else out of balance. So removing 32 says, hey, that's great. There's nothing here now. 17 says, now I'm a leaf node. I've got to be balanced. I had a height of 2 before, and I lost my only child, so now I must be of height 1. I can report that back to my parent who did the insertion. So 44 gets the report that after this deletion, your left child is of height 1. 44 can say, well, what's the height of my right child? Oh, it's 3. I must be out of balance. I need to be rotated left about here. So we end up needing a rotate left about 44, and the 44 goes down. 62, its right child comes up, and since 62 already had a left child, it has to pitch that off to be the right pointer of the old parent. So that's where you see this snip of 50, and then it gets transferred over to catch 44 and attaches right there. Now I've got another sparse-ish looking tree, but it's still balanced, and now it's minus that 32 node that we were meaning to delete. All right? We did that with one fix, right? We continue to work our way up, right? We start from the deletion point. That's where we deleted. Obviously, there's nothing to fix there. 17 was fine. Then we got to the root, right? After we rotated, we fixed things at the root, and all we could have done from there on is realize that everything else over here on the right-hand side was not part of the problem. So we've attached everything that we needed to do, and our tree is now balanced. That was a pretty trivial removal. Let's try something a little bit more challenging. Okay, now 62 is the top. What happens if we remove 62? All right? So to remove 62, we have to first find the in-order successor. That means go right once and go left until you can't go left anymore. That is, of course, 78. That's the in-order successor. So I'm going to replace 62 with that 78, right? And you see this replace looks like that. I copied 78 over 62, and my tree has this current duplicated element here in 78. But I'm going to remove that because that's the node that I want to remove. It's my in-order successor. It has only one child, so I can replace that 78 with its child. So I remove 78 and promote 88, and now I've got this perfectly good binary search tree, but it's not a good AVL tree, because if you look at what I did, I changed the height. 44 knew what its height was. 78, as it moved into this position, already knew what its left subtree's height was. It was already 3. It hasn't changed. We're only working on the right side. So it's 3 over here, and now 1 over there. That get me a balance factor of 2, right? It's a +2 balance factor, and that's not good. So now I've got to do what? I've got to do a rotation. I've got to do a rotation. And how am I going to do that rotation? Which rotation is it? It's going to be a right rotation eventually, because I've got a +2. I need to push some things over to the right-hand side. But where do I get that from? There's a balance factor of +2 there. If I look at my balance factor here on 44, balance factor on 44 has got a -1 balance factor. All right, so there's a zigzag. In order for me to fix this, I'm going to have to first rotate left around 44, followed by a rotate right around 78. And then I do this double rotation. There's my first step. You see now things have gotten worse. But after the rotation, it looks like that. So in both of these cases, both of my removals, I removed the node, and one was a fairly simple removal that caused an imbalance. I was able to fix it with one rotation. The other one was a bit more complicated removal because it was a more internal node. But even after removing an internal node, I still only needed to do one fix, and everything was fine. So once again, we're at this constant amount of work, right? In the trivial example, we only had to do one rotation. In the more complicated example, we did 2 rotations. But if we think of a fix as being 1 rotation or 2 rotations, there was still only one fix in both cases. So after an insertion, we need at most one fix. After a removal, we need at most one fix. And since those fixes are a constant amount, all I'm doing is making insertion and removal only slightly slower, but still the same time complexity. So that's what I get. I get this constant additional amount of work to maintain my log n depth at all times, best case, worst case, and average case. So the summary of the entire tree traversal, the traversal of all the trees that we've talked about, is that we've got the BST. Our worst case insert or search would be linear if we didn't deal with balance. We could insert our way into a bunch of sticks if we only worried about the binary search tree property. The AVL tree, we added additional work to there. I'm getting reflections here. All right. Go back. Review. Fix here. We fix our way up to the root. That's what we did. I misspoke on that one. So, in fixing my way up to the root on this previous example, right? I started here at my deletion point. Fixing my way up to the root, things were good. And that's right. Because this fixing takes place inside of the actual removal, as I recurse my way through removing some object, right? I'm going to work my way back up to the root while I'm doing my balancing. Right, so after I've done this fix here, I guess this example doesn't really show it too great. After we've done this fix, I'm at the situation where I've rotated right around 8. My check balance is going to continue to work its way up to the root. Every time it works its way up to the root because it's part of the removal. So in this case, we may have to do another fix, right? You fix your way all the way back up to the root, which adds some additional amount of work. How much work? At most, a constant amount of work for every node. And since we're already in a tree whose height is no more than log n, even if I have to do a rotation to fix myself all the way back out after a removal, I still only end up adding a constant amount of work for every fix. So it ends up, no matter how many fixes I have to do, can't be more than log n fixes because I'm log n depth. So slight misspeak there. Not too much to worry about, however. All right. Because my AVL tree gives me this worst case insert, search, or even removal of log n, when I guarantee this height balance property, that's why we like the AVL trees. To be certain, an AVL tree in its operations, they're the same time complexity. They're the same big O as a BST, but they are a little bit slower because we do have to check to see if we're going to do our check and balance. And in the cases where imbalances crop up, we've got to do an additional amount of work, but it's not a change of complexity. So then I end up with my AVL tree having search, insert, remove, all log n. If I want to use an AVL tree to do a sort, since I can do all my insertions in log n, there's n of them, n times log n gives me an n log n build of the tree plus a big O of n linear traversal to do an in-order traversal. So I can use an AVL tree to always guarantee that I've got an n log n sort. Finally, we talked about the rotations. We called them a constant amount of additional work because it was this interchanging of 2 nodes while updating 3 pointers. That's a constant amount of work. Even if I was to do a double rotation, I might have to do that twice, but no more than twice. All right. This one is always fun at parties. Maybe later when we return to campus and social distancing parties begin, you can screencast some Visual Algo, right? This wonderful site that shows you how these algorithms work, and you can sort of really visualize them. That's part of the thing in there. So we're going to go and check on how this works. We'll go see what Visual Algo gives us, right? And I think that link is going to take me right to the binary search tree. That's good. And what I want to do is you can look through, there's great discussion on this stuff. And what I really want to do, though, is make sure I'm working with an AVL tree, because this has got my balanced situation here. Then I can pop down to this insertion section, and let's add some nodes in here. So one isn't going to throw me out of balance, but if I add in a comma and 90, let's see how that looks. So insert 1, 77, and 90, and go. You can see the steps that go through there. It tells you what's happening, it tells you about the comparisons. There's a check of our way back up to the root. Life is good. Insert 77. After the insertion, check and balance up to the root happens. Now we're going to do an insertion of 90. 90 throws my check and balance off. I'm going to have to do a rotation. There's my rotation. Check and balance my way back up to the root. Life is good. So this is a great way to sort of really visualize these things as you go. You can pick that entire list of, you can create that entire list of insertions that we did in the slides, right? That was something like, I said 3, 2, 1, 4, 5, 6, 7, 16, 15, and 14. That sounds good. And let's go. So this is exactly what we already did on the slides, but you can see here Down in the lower right, I've got a discussion of what's going on. If you look in the lower left there, I've got a speed control if you want to slow down this insertion. I can also grab sort of like my progress bar in the middle to go back to a step if I wanted to see something. It's a pretty powerful tool in terms of trying to get some understanding. There's our second rotation, sorry. And put in 7. We need to rotate around 2 to fix things here. 16, 15, and 14 coming in. After 7 gets a fix up there. So yeah, this is a great place to figure out what's going on with some of these algorithms. There's other containers in here as well if you'd like to look at those. Here comes 14. 14 is going to give us the zigzag underneath 7 and 15. So we'll first rotate left around 7. And rotate. Yeah, there we go. All right. The tree is now balanced. Excellent. So have a check on that one. You can do a bunch of stuff there, right? So have some fun with it. Make sure you understand what's going on. Make sure you can ask yourself what kind of questions might be fired at me on an exam. How might I prove that I understand how these rotations work? How might I prove that I understand the complexity of them and that sort of thing? So that is AVL trees, and that's going to conclude our discussion of trees in general.